Imagine you are standing on a beach at night. The water is calm, and the sky above you is completely clear. No light pollution, no clouds, nothing between you and the full, staggering depth of the universe. You tip your head back and you look up. What you see, even with the naked eye, is overwhelming. Stars beyond counting, scattered like salt across black velvet, and behind them, if you look carefully, the faint, ghostly smear of the Milky Way arcing from horizon to horizon. It looks infinite. It feels infinite. And somewhere in the quiet of that moment, a thought begins to form, the way it always does when human beings stand underneath an open sky and let themselves really feel the weight of what they're seeing. What if we could go there? What if we could take a ship, point it at one of those lights, and just go? It's the oldest dream in the human repertoire. Long before we had rockets, long before we had telescopes, long before we even had writing, our ancestors were sitting under skies just like this one and wondering the same thing. The stars have always felt like destinations. They've always felt like somewhere you could arrive at if only you had the right vehicle, the right fuel, the right amount of courage. And now, in the 21st century, we have finally developed enough science to understand exactly what it would take to make that journey. We have done the math. We have run the simulations. We have pushed our equations to their absolute limits. And what the math tells us is both magnificent and quietly devastating. What it tells us is that the universe is so incomprehensibly large and the laws of physics so absolute and unyielding that the vast majority of what exists out there will never be visited by anything bearing a human origin. Not in 1,000 years, not in 1,000,000, perhaps not ever. We are, for all practical and perhaps eternal purposes, locked inside a tiny, warm corner of an impossibly vast cosmic structure, and the walls of that corner are not made of metal or stone. They are made of physics itself. This is the story of why you will never leave your cosmic neighborhood. Not because we lack ambition, not because we lack intelligence, but because the universe, it turns out, does not care about our ambitions at all. If you find yourself genuinely moved by ideas like this one, we'd love for you to subscribe and hit that like button. It helps us keep making content that reaches for the stars, even when the stars are impossibly far away. Let's start small. Let's start here on Earth, because it's easy to forget just how large this planet is when you spend most of your life looking at a map on a phone screen. The Earth has a circumference of roughly 40,000 kilometers at the equator. If you were to walk that distance without stopping, moving at a brisk human pace, it would take you somewhere in the neighborhood of a year, and that's just to go around the outside. The interior of the planet, from crust to core, plunges nearly 6,400 kilometers deep into temperatures and pressures that no human technology has ever directly reached and likely never will. We live on the thin, cooled skin of a planet we have barely scratched, and yet, in the context of the solar system, the Earth is barely a dust mote. To get from here to the moon, our closest natural neighbor in space, you would have to travel about 384,000 kilometers. That sounds like a lot, until you actually try to visualize it. If the Earth were the size of a basketball, the moon would be a tennis ball, sitting about 7 meters away. The Apollo astronauts made that journey in 3 days. riding technology that by modern standards looks almost charmingly primitive. It was one of the most extraordinary feats in human history, and in cosmic terms, they barely moved. Then there's Mars. Mars is the planet we most often hear described as humanity's next frontier, the next step, the place we'll build cities and terraform and call a second home. And in a solar system context, Mars is indeed our neighbor. But neighbor is a word that does very dangerous things to our intuitions here. Even at its closest approach to Earth, Mars sits about 55 million kilometers away. At its farthest, it's closer to 400 million kilometers. The fastest spacecraft ever launched from Earth, the Parker Solar Probe, briefly touched speeds of around 690,000 kilometers per hour as it swooped close to the Sunday. At that kind of velocity, a velocity so extreme that the human body couldn't possibly survive the acceleration needed to reach it, a trip to Mars at closest approach would still take a few months. A trip to Mars at farthest approach would take considerably longer. These are not small numbers. These are numbers that break the casual assumptions most of us carry about space travel without even realizing we carry them. We've grown up on science fiction that treats the solar system like a neighborhood you can drive across on a Sunday afternoon. The reality is that even our own solar system, the tiny gravitational bubble of space dominated by our single star, is almost beyond human comprehension in its size. Consider Neptune, the outermost of the 8 recognized planets. Neptune sits, on average, about 4.5 billion kilometers from the Sunday. When Voyager 2 was launched in 1977 and sent on a grand tour of the outer planets using carefully calculated gravitational slingshots that took advantage of a rare planetary alignment, it took 12 years to reach Neptune. 12 years, traveling at tens of thousands of kilometers per hour, and it was still crawling across the solar system like a beetle crossing a highway. Today, Voyager 2 is the second most distant human-made object ever created. It has been flying continuously for nearly 50 years. It has now left the region dominated by the solar wind and crossed into what scientists call interstellar space, and it is still, by the scale of what lies ahead, essentially sitting in our front yard. Beyond Neptune, the solar system doesn't simply end. It trails off into a vast, diffuse cloud of comets and icy debris called the Oort cloud, a spherical shell of frozen leftovers from the formation of the solar system that extends perhaps 1 to 2 light-years from the Sun in every direction. The Oort cloud has never been directly observed. It's too distant and the objects in it too small and dark to detect with our current instruments. But we know it's there because of the long-period comets that occasionally get nudged inward by gravitational interactions and swing through the inner solar system, briefly blazing into visibility before retreating back into the dark. These comets have been traveling for millions of years to reach us. That right there should give you pause. The objects that share our solar system, that are gravitationally bound to our sun, that are, by any reasonable definition, part of our neighborhood. Some of them take millions of years just to complete a single orbit. That's the scale of our own backyard. And our backyard, large as it is not where the really challenging distances begin. The real distances begin at the nearest star. Proxima Centauri is the closest star to our Sunday. It's part of a three-star system called Alpha Centauri, which has become a kind of cultural shorthand for the nearest place we might go. Proxima Centauri even has a planet in its habitable zone, a world called Proxima b, which has generated enormous excitement among scientists and dreamers alike. And Proxima Centauri is, by stellar standards, right next door. It is our nearest cosmic neighbor. It is 4.24 light-years away. Now, that phrase, light years, is another one that our brains tend to absorb without truly processing. A light year is not a unit of time. It's a unit of distance. Specifically, it's the distance that light travels in 1 year. And light moves fast. Light moves so unimaginably fast that it circles the entire Earth 7.5 times in a single second. In 1 second. Light could travel from New York to Los Angeles and back about 400 times in the time it takes you to blink. It crosses the distance from the Earth to the Moon in about 1.3 seconds. It crosses the distance from the Earth to the Sun in about 8 minutes. 1 light year, the distance light covers in an entire year, moving at that speed, is approximately 9.46 trillion kilometers. Write that out. 9,460 billion kilometers. And Proxima Centauri is 4.24 of those. If you could somehow drive to Proxima Centauri in a car moving at highway speed, the trip would take about 50 billion years. The universe itself is only about 13.8 billion years old. You would need to have started that drive more than 3 times before the Big Bang for it to be arriving now. But let's be more generous. Let's use the fastest spacecraft ever built. Voyager 1, which has been traveling through space since 1977 and is now the most distant human-made object ever created, moves at roughly 17 kilometers per second relative to the Sunday. At that speed, to reach Proxima Centauri, it would take approximately 73,000 years, not 73,000 days. 73,000 years. That's longer than recorded human history by many multiples. That's longer than the time since our ancestors painted the walls of the Lascaux caves in France. We would need to launch a mission and then wait through the entire span of human civilization several times over before it arrived. And Proxima Centauri is the closest one, the nearest star. Everything else is farther. This is the first great wall of cosmic exploration, the sheer, brutal, arithmetic fact of interstellar distance. The universe has not arranged itself at scales convenient for biological creatures with lifespans measured in decades. A human life is, from the perspective of the cosmos, almost comically brief. Even a civilization's lifespan, if we're generous and imagine human civilization persisting for another 10 or 20,000 years, is barely a rounding error on the timescales involved in crossing even a modest portion of the galaxy. So the obvious question becomes, what if we went faster? What if we built engines so powerful, so efficient, so far beyond anything we have today, that we could get our speed up to something meaningful? What if we could travel at, say, 10% of the speed of light? That would be roughly 30,000 kilometers per second, many orders of magnitude faster than anything we've ever built. At that speed, Proxima Centauri would be reachable in about 42 years, a human lifetime. Still long, but imaginable. A person could be born, grow up, dedicate their life to the journey, and arrive at another star before they died. And then what? They would find a destination. They would transmit their discoveries back to Earth, and the signal, moving at the speed of light, would take 4.24 years to arrive. And by the time it did, any response sent back would take another 4.24 years to reach the ship. Communication across interstellar distances is not a phone call. It's more like carving a message into stone, dropping it into the ocean, and hoping the tides carry it somewhere in the right direction eventually. But forget communication. Let's just focus on the travel itself. 10% of light speed. Could we achieve it? The honest answer is that with our current technology and our current understanding of engineering, we cannot. Not even remotely. The fastest humans have ever traveled, relative to Earth, is the crew of Apollo 10 during their return from the Moon, who reached about 11 kilometers per second. 10% of light speed is 30,000 kilometers per second. That's a factor of nearly 3,000 faster than the fastest humans have ever gone. Every system on the ship, the engines, the fuel, the structural integrity, the life support, the navigation, the shielding would need to operate at levels of performance so far beyond anything we've demonstrated that describing the engineering gap as challenging would be almost absurdly generous. And then there's the problem of fuel. This is where things become genuinely painful for anyone who has ever wanted to believe in interstellar travel. Because the amount of energy required to accelerate a spacecraft to a meaningful fraction of light speed is not just large, it is, by any measure of our current civilization's energy production, essentially infinite. Let's think about this carefully. To accelerate any object to higher and higher speeds, you need more and more energy. This is basic Newtonian mechanics, intuitive enough that even without the math, most people grasp it instinctively. But the relationship between speed and energy isn't linear, it grows. As you push an object to higher and higher fractions of light speed, the energy required doesn't just climb, it explodes. Consider a spacecraft massing 10 tons, which is quite small. By modern standards, the International Space Station weighs over 400 tons. To accelerate that 10-ton spacecraft to just 10% of light speed would require an energy output roughly equivalent to the total amount of energy the United States uses in millions of years. Not all at once, but still, the energy budget of an entire civilization's power grid running for epochs just to get a small ship moving at a fraction of the speed you'd need. And here's the cruel kicker. That's only one way. You'd need to decelerate at the other end too, which requires the same energy expenditure all over again. And if you want to come home, you're doing it twice more. A return trip to Proxima Centauri at 10% of light speed would demand an energy investment that staggers the imagination of any honest engineer. People have proposed solutions to this. Antimatter engines, which would be vastly more efficient than chemical rockets. Laser sails that use focused energy beams to push lightweight probes. Fusion drives. Exotic concepts like the Alcubierre warp drive, which doesn't accelerate the ship itself, but warps the space around it. All of them are interesting. All of them face profound physical or engineering barriers that make them, at best, theoretical possibilities rather than practical engineering proposals. Antimatter is real. but producing it in useful quantities would require an energy infrastructure that doesn't exist and might never exist. Laser sails work beautifully in equations, but become increasingly difficult to operate at interstellar distances, where keeping a beam focused on a tiny moving target across trillions of kilometers requires a precision that borders on the physically impossible. The Alcubierre drive, meanwhile, appears to require something called exotic matter, a form of matter with negative energy density that has never been observed in nature and may not exist at all. And we haven't even introduced the deepest problem yet, the problem that no engineering solution can touch, the problem written into the fundamental structure of space-time itself. We call it special relativity, and it is the second Great Wall. Albert Einstein published the theory of special relativity in 1905, and in doing so, he fundamentally changed what it means to move through the universe. Before Einstein, people imagined space and time as separate, absolute things, a stage on which the drama of the universe played out. After Einstein, we understood that space and time are woven together into a single fabric, and that the experience of space and time is not fixed but depends on how fast you are moving relative to other things. The faster you move, the more time itself slows down for you relative to a stationary observer. This is not a metaphor or a philosophical abstraction. It is a physical reality, measured in laboratories and confirmed by GPS satellites, which have to account for relativistic time differences every single day, or they would quickly drift out of accuracy. The closer you get to the speed of light, the more extreme the time dilation becomes. If you were to travel at 99% of light speed, time on your ship would pass at roughly 1/7 the rate of time on Earth. You would age 7 times more slowly. If you took a 10-year journey at that speed, as measured by the ship's clocks, 14 months would pass for you, but 70 years would pass back home. Everyone you knew when you left would be elderly or dead. The world you returned to would be a world you'd never seen, filled with people you'd never met, speaking a culture that had evolved in your absence. This gets more extreme as you approach light speed. At 99.9% of light speed, the ratio gets even more severe. At 99.999%, more extreme still. In theory, a sufficiently advanced ship moving close enough to light speed could, from the perspective of its passengers, cross the galaxy in a human lifetime. The crew would age only decades, while millions of years passed outside. They could reach the other side of the Milky Way and return to find Earth, if it still existed at all, populated by beings as remote from us culturally and biologically as we are from the first primitive fish to flop onto dry land 375 million years ago. Time dilation is real. The physics is not in dispute. But notice what this solution actually offers. It doesn't solve the problem of distance. It doesn't make the stars closer. It doesn't make travel fast in any absolute sense. It simply rearranges who bears the cost of the journey. The crew pays with their personal time. Everyone else pays with all the time in the world. Interstellar travel via relativistic speed is not a round trip in any meaningful human sense. You can't go and come back. Not really. Not to anything you'd recognize as the world you left. And even this profoundly bittersweet option requires achieving velocities so close to light speed that the energy requirements move from staggering to utterly unfathomable. But there's a more fundamental reason why the speed of light is not just a very high speed limit we haven't yet managed to engineer our way past. It's not like the sound barrier, which seemed impossible to cross until someone clever figured out the right shape for a wing. The speed of light is a speed limit baked into the structure of the universe at the most fundamental level. As an object with mass accelerates toward light speed, its relativistic mass, the effective inertia it has, increases. The faster it goes, the more energy you need to accelerate it further. The more energy you pump into it, the faster it goes, but also the heavier it effectively becomes, requiring more energy still. As the speed approaches the speed of light, the energy required to push it any faster approaches infinity. Actual, literal, mathematical infinity. You cannot reach the speed of light with a spacecraft that has any mass at all, not with better engineering, not with more fuel, not with any technology, because the constraint isn't technological. It's mathematical. It's the way the universe is structured at the most fundamental level. Only things without mass photons, the particles of light, can travel at light speed, and they have to. Photons cannot travel slower than light speed any more than a baseball can travel faster. It's not a coincidence. It's the geometry of space-time itself, so you cannot exceed light speed. And at light speed, the universe is still heartbreakingly large. Even at light speed, a journey from one side of the Milky Way galaxy to the other would take 100,000 years. A journey to the Andromeda galaxy, our nearest large galactic neighbor, would take 2.5 million years. A journey across the observable universe would take 93 billion years, more than 6 times the current age of everything that exists. This is where many explanations of interstellar distance stop, because those numbers are already so enormous that adding more feels almost sadistic. But the full story is even more confronting than this, because we haven't yet talked about what the universe is actually doing while we're sitting here imagining these journeys. The universe is expanding. In 1929, Edwin Hubble made one of the most consequential discoveries in the history of human thought. He found that the distant galaxies were moving away from us, and that the farther away a galaxy was, the faster it was receding. The universe is not static. It is not a fixed stage. It is an expanding structure in which the distance between galaxies grows over time, not because the galaxies are moving through space, but because space itself is stretching. The fabric of space-time is expanding, carrying galaxies along with it like raisins in a rising loaf of bread. And then, in 1998, things got significantly stranger. Astronomers studying distant supernovae discovered that the universe isn't just expanding, it's accelerating. Something is pushing it apart faster and faster. We call this mysterious force dark energy. We have essentially no idea what it is. We know it exists because the math only works if we include it, and it appears to make up roughly 68% of everything in the universe. It's the majority of everything, and we can't detect it, can't interact with it, and can't explain it in any deep sense. All we know is what it does. It drives the accelerating expansion of space. The consequence of this is profound and quietly terrifying. There are galaxies in the universe right now that are already beyond our reach. Not beyond our reach in the sense that they're very far away and it would take a long time to get there. Beyond our reach in the sense that even if we launched a spacecraft today moving at light speed, the expansion of space between here and there is happening faster than light itself can cover the distance. Those galaxies are, in the most literal possible sense, leaving the observable universe. They are receding faster than anything can follow. They will eventually pass beyond a boundary called the cosmic event horizon, beyond which no signal, no information, and no spacecraft could ever reach them or return from them. This is a one-way door built into the structure of space-time. It is closing as we sit here. The observable universe, already incomprehensibly vast, is slowly shrinking in terms of what is, even in principle, reachable. Future civilizations, if they exist billions of years from now, will inhabit a universe that looks dramatically emptier than ours. The galaxies we can see from here will have disappeared beyond the horizon. Those future beings might look up at their skies, see only a handful of galaxies in their local group, and conclude that their galaxy is alone in an otherwise empty cosmos. They'll be wrong, but there will be no way for them to know it. We have the advantage of living at a relatively early moment in cosmic history, when the evidence of the Big Bang is still visible in the form of the cosmic microwave background radiation, and when many distant galaxies are still within the observable universe. But even this relatively privileged moment is not enough to make the cosmos reachable. Even now, the observable universe contains an estimated 2 trillion galaxies. 2 trillion. And essentially all of them are, in any practical sense, permanently, irretrievably beyond our reach. Let's bring this back to something more immediate, because it's possible to lose yourself in these astronomical numbers and forget that the same barriers apply on much smaller scales. Let's go back to our nearest stellar neighbor, Proxima Centauri, and think again about what reaching it would actually require, not in terms of physics, but in terms of engineering and human endurance. Suppose we forget about the energy problem, just set it aside for a moment, and imagine that some future civilization has somehow solved it. They have an engine capable of accelerating a spacecraft to a meaningful fraction of light speed. What else would they need to solve? The list is long, and each item on it represents a civilization-defining engineering challenge in its own right. There is the problem of interstellar medium. Space is not empty. It is filled with a thin but non-trivial distribution of gas, dust, and particles. At low speeds, this is irrelevant. But at high speeds, even tiny particles become devastating. At 10% of light speed, a grain of sand hitting your spacecraft would release energy roughly equivalent to a nuclear bomb, not a small bomb. The kind of bomb that levels a city. Protecting a spacecraft from this continuous, high-energy bombardment over a journey lasting decades would require a shield of extraordinary capability, something fundamentally different from any material science we currently possess. There is the problem of navigation. Interstellar space is not mapped with the precision that would be needed for a high-speed journey. Stars move. The position of Proxima Centauri relative to the Sun changes over time as both stars orbit the galactic center. A spacecraft launched today at high speed toward where Proxima Centauri is now would need to aim at where Proxima Centauri will be when the ship arrives, decades in the future. The margin for error in that calculation, over 4.24 light-years, is essentially zero. There is the problem of communication and human psychology. A crew of humans locked in a small vessel for decades, isolated from the rest of humanity by distances that make real-time communication impossible, relying entirely on each other and their own resources, would face psychological pressures we have never had to design for. We have experience with long-duration spaceflight from the International Space Station and experiments like Mars 500, which simulated a long-duration Mars mission. The psychological challenges, even at these relatively short timescales, are significant. Extrapolate that to decades, to knowing that everyone you've ever known is aging and dying back on Earth while you float through the dark. The psychological design challenge is unlike anything we've ever faced. There is the problem of biological degradation. Humans did not evolve for zero gravity, high radiation environments, or existences confined to small metal tubes. Space flight is hard on the human body in ways we're still discovering. Bone density loss, muscle atrophy, vision problems caused by fluid redistribution in microgravity, immune system suppression, radiation exposure that significantly increases cancer risk. These are all real, documented problems for astronauts who spend just 6 months on the space station. A multi-decade interstellar voyage would require either solving all of these biological problems, which represents challenges at the frontier of medicine, or transporting humans in some form of suspended animation, which remains entirely in the realm of science fiction, with no demonstrated scientific pathway to reality. And then there is perhaps the most quietly devastating problem of all. What happens when you arrive? Suppose the ship reaches Proxima Centauri. Suppose it has found its way to Proxima b, the planet in the habitable zone. What does the crew find? The word habitable zone sounds welcoming, but all it actually means is that the planet is at a distance from its star, where liquid water could theoretically exist on its surface, given the right conditions. Proxima b orbits a red dwarf star, a type of star very different from our Sun day. Red dwarfs are prone to violent stellar flares that strip away planetary atmospheres and bathe nearby planets in intense radiation. Proxima b is almost certainly tidally locked, meaning one face always points toward the star and the other always faces the dark, creating a world of perpetual day on one side and perpetual night on the other. The conditions on Proxima b could be anything from marginally habitable to utterly lethal. We don't know. We won't know with any precision until we send something there. But suppose it's habitable. Suppose the crew lands on an alien world orbiting another star. They are 4.24 light-years from Earth. They are, in every meaningful sense, on their own. Any signal they send home will take 4.24 years to arrive. Any help, any resupply, any rescue, all of it is more than 4 years away by the fastest possible communication and infinitely further away by any form of physical travel. The crew of this ship would be, for all practical purposes, a separate civilization. Their decisions, their discoveries, their fates, all of it would be theirs alone, for good or ill. This is not a new problem in human history. Exploration has always involved isolation. The Polynesian navigators, who crossed the Pacific in outrigger canoes, were separated from their home islands by months of open ocean with no communication at all. The early European explorers who crossed the Atlantic were cut off from news for months or years at a time. Humans have demonstrated, repeatedly, an extraordinary capacity for enduring that kind of isolation in the service of discovery. It's one of the things that makes our species remarkable. But the scale of interstellar isolation is different in kind, not just degree. The Polynesian navigator, who lost sight of his home island, could, in principle, turn around and find it again. The crew of an interstellar ship, even if they turned around immediately, would spend decades retracing their path, and the world they returned to would not be the world they left. It would be a world that had moved on without them, that had changed in ways they couldn't predict, that might not have a place for them anymore. This is perhaps the most human dimension of the interstellar problem, and it's the one that science fiction most consistently underplays. It's not just the physics that makes interstellar travel hard, it's the irreversibility. Every step away from Earth is a step that cannot be fully undone. The distances involved don't just challenge our engineering, they challenge our psychology, our sense of belonging, our fundamental human need to be connected to a community, a home, a history. We are social animals. We evolved in small groups, in tight communities, in environments where the people who mattered to us were close enough to touch. We carry that evolutionary legacy in every cell of our bodies, in every instinct that fires when we feel lonely or frightened or uncertain. Space, by its nature, is the most extreme possible violation of every one of those instincts. It is cold and dark and silent and utterly indifferent to whether we live or die. And yet, there is something about all of this that cuts in two directions. Because the same physics that makes interstellar travel so impossibly difficult also reveals something breathtaking about the universe we inhabit. The same equations that show us the walls of our cosmic cage also show us the true scale of what lies beyond those walls, and that scale, even if we can never experience it directly, is itself a kind of gift. Think about what it means that we can know this. We are creatures who evolved on a small planet orbiting a medium-sized star in the outer reaches of a fairly ordinary spiral galaxy. We have existed as a recognizable species for perhaps 300,000 years. We have had writing for a few thousand years. We have had modern science for a few hundred. And in that extraordinary short span of time, we have developed the intellectual tools to understand the size of the universe, the speed of light, the curvature of space-time, the accelerating expansion of the cosmos. We have discovered that there are 2 trillion galaxies beyond our own. We have identified planets around other stars. We have detected the faint echo of the Big Bang itself, still humming in the background radiation of space after 13.8 billion years. We cannot go to these places, but we can know they exist. We can understand them in a way that goes far beyond merely naming them or mapping them. We can describe the physics of a star-going supernova, the dynamics of a black hole's event horizon, the life cycle of a galaxy. We do this from a small, warm planet, using brains that evolved to track animals across a savanna and pick fruit from trees. The fact that those brains have been able to reach across billions of light years and make sense of what's out there, that is, if you'll allow a moment of unguarded wonder, absolutely astonishing. But there's another layer to this, and it's the layer that tends to bring people up short when they really sit with it. The question isn't just whether we can travel to other stars. The question is whether anyone can. Whether any form of life, anywhere in the universe, faces the same barriers we do, or whether there is some way around them that we simply haven't discovered yet. This is where we have to be intellectually honest in a way that can feel uncomfortable. As of today, we have no evidence that the speed of light has ever been exceeded by anything. We have no evidence that wormholes, those hypothetical shortcuts through space-time, exist in any form accessible to a traveler. We have no evidence of any technology, natural or artificial, that circumvents the energy constraints of relativistic travel. The laws of physics, as we understand them, appear to be universal. They apply as completely on the other side of the galaxy as they do in our laboratories here on Earth. We have tested these laws to extraordinary precision, and they have never failed. This means that if there are other civilizations out there, and the size of the universe alone suggests the probability is very high they face the same walls we do. A civilization on a planet orbiting a star 100 light-years away cannot reach us in less than 100 years, even in principle. They cannot exceed light speed any more than we can. The galaxy, for all its 200 to 400 billion stars, may be filled with islands of life that are permanently separated from each other by the geometry of space-time. The Fermi paradox, the question of why, given how large and old the universe is, we haven't detected obvious signs of other civilizations, may have its answer right here. Not because civilizations are rare, but because the distances between them are so large and the speed of light so absolute that even a galaxy teeming with intelligence would look, from any given vantage point, essentially empty. We may be surrounded by neighbors we can never meet. We may be embedded in a cosmos where the fundamental rules of physics ensure that consciousness, wherever it arises, always remains local, always remains bounded, always remains, in the end, alone, in its corner of the universe. This is, if you let it land, one of the most profound ideas in all of science. Not because it's hopeless, it isn't, but because it reframes what the universe actually is. We have long imagined the cosmos as a kind of frontier, a vast territory waiting to be explored, mapped, and inhabited by beings bold enough to reach for it. We have inherited this framing from our own history, from the Polynesian explorers and the European age of sail and the American westward expansion. We are a species that moves. We are a species that explores. We have always assumed that if the frontier exists, we will eventually cross it. But what if the universe is not a frontier at all? What if it is instead something more like an artwork or a dream, something vast and extraordinarily beautiful that exists to be perceived and contemplated from where you stand, rather than to be physically conquered and occupied? What if the correct relationship between a living mind and the universe is not that of an explorer crossing a territory, but something more like a person standing in front of a painting that is larger than any building ever built, taking in what they can see, knowing that most of it is beyond their view, and finding that this limitation does not diminish the experience but somehow intensifies it? The stars we see with the naked eye on a clear night are almost all within a few thousand light-years of Earth, a tiny, tiny bubble within a galaxy 100,000 light-years across. Most of those stars were already there when our ancestors first looked up at them. The light reaching our eyes right now left some of those stars before the Egyptian pyramids were built. And yet, in all that time, those stars have moved across the sky by amounts so small as to be essentially imperceptible to the naked eye. The sky our great-great-great-grandchildren will see 1,000 years from now will look almost identical to the sky we see tonight. The stars feel eternal, even though we know they're not. They feel close, even though they're impossibly far. They feel like they're waiting for us, even though they're utterly indifferent to our existence. That tension between how the stars feel and what they actually are is the defining emotional experience of living in a universe that is too large to explore. Every civilization capable of looking up and understanding what it sees must eventually reckon with this. The cosmos is not scaled for life. It is not designed with exploration in mind. It is not a place that invites visitors. It is a structure that arose from the quantum fluctuations of a hot, dense beginning, expanded under the influence of forces we barely understand, and produced in the spaces between galaxies, on the surfaces of small rocky worlds orbiting ordinary stars, the extraordinary accident of minds capable of comprehending it. We are that accident. We are the universe, looking at itself through eyes made of stardust. The iron in our blood was forged in the hearts of stars that exploded billions of years before the sun was born. The calcium in our bones, the oxygen in our lungs, the carbon that forms the backbone of every molecule in our bodies, all of it was created in the nuclear furnaces of stars and scattered through space by the violence of their deaths. We are not separate from the cosmos. We are continuous with it. We are made of it in the most literal possible sense. And yet we can know things about the cosmos that the cosmos itself cannot know about itself, at least not in the way we know them. A star does not know it is a star. A galaxy does not contemplate its own structure. Only we, as far as we know, only we have developed the capacity to look out at the universe and understand what we're seeing, to trace the physics of distant events from the safety of our own small corner, to feel the weight of what the numbers mean. There is something deeply moving about this, and something deeply humbling. We have this extraordinary gift of understanding, and we are confined to an extraordinarily small domain. We can see out to 13 billion light years and understand what we're seeing, but we cannot go there. We cannot even go very far in any direction. Our nearest stellar neighbor is 4.24 light years away, and reaching it with anything like current technology or reasonable extrapolations of future technology remains in the realm of the fantastically difficult. The solar system, our actual solar system, the gravitational domain of our sun, is the territory we might, over the coming centuries and millennia, realistically inhabit and explore in person. Mars in this century, perhaps. The asteroid belt, eventually. The moons of Jupiter and Saturn, with their subsurface oceans and complex chemistries, might represent the next great frontier of human exploration in the physical sense. Europa, with its vast ocean hidden beneath an icy crust, could harbor life. Titan, Saturn's largest moon, with its rivers and lakes of liquid methane and its complex organic chemistry, is unlike any world we've ever seen. Enceladus, with its geysers of water vapor erupting from a warm, salty ocean beneath its frozen surface, is one of the most compelling places in the solar system for the search for life. These worlds are within reach, not easily, not cheaply, not without extraordinary technological development, but within reach in a way that Proxima Centauri is not. The solar system is a genuinely rich territory for exploration, with hundreds of worlds of varying character, chemistry, and potential. And the sheer scientific and philosophical importance of finding any form of life, even microbial, within our own solar system, would be the most significant discovery in human history, dwarfing any question about interstellar travel by the sheer weight of what it would tell us about the nature of life itself. So the picture is not purely one of limitation and loss. The cosmic neighborhood in which we are permanently, inescapably embedded is itself a place of extraordinary richness and complexity and scientific depth. We have a sun we barely understand, with a magnetic field that produces spectacular phenomena we're still working to explain. We have 8 planets of wildly different character, from Venus, the hellish, cloud-shrouded twin of Earth that became the solar system's cautionary tale about runaway greenhouse warming, to Jupiter, the gas giant colossus, whose red spot is a storm that has raged for hundreds of years, and whose gravitational influence has profoundly shaped the architecture of the entire solar system. We have moons more geologically active than many planets, asteroid belts with more total surface area than you might imagine, comets that serve as messengers from the frozen early days of the solar system, and a star whose energy has sustained life on Earth for 4 billion years and will continue to do so for another 5 billion more. Our neighborhood is not small in any meaningful sense. It is only small in comparison to what lies beyond it, and what lies beyond it is so vast that the comparison itself becomes almost meaningless. Perhaps the most useful way to think about this is not in terms of what we cannot reach, but in terms of what our reach actually means. We are, as a species, not even 1 million years old. Modern technological civilization is perhaps 300 years old, depending on how you count. We have had the capacity to leave our own planet for less than a century. In those few decades, we have sent machines to every planet in the solar system. We have landed on the Moon and on Mars. We have dropped probes into the atmospheres of Jupiter and Venus. We have flown spacecraft past Pluto and sent robots to study the surface of an asteroid and bring back samples. We have put a telescope in space that can detect the atmospheres of planets orbiting other stars. We are, by any fair assessment, doing extraordinarily well for the age we're at. The question of whether we will ever cross the interstellar gulf is not one we can answer from here. Not because the answer is unknowable in principle, but because the answer depends on things that haven't happened yet. It depends on whether the physics we currently understand is the complete picture, or whether there are undiscovered phenomena, perhaps involving quantum mechanics, perhaps involving aspects of space-time we haven't fully mapped that change the calculus in ways we can't yet anticipate. Science has surprised us before. The history of physics is a history of periodic, stunning revisions to what we thought was a complete picture. Newtonian mechanics seemed complete until quantum mechanics revealed an entirely different layer beneath it. Classical electrodynamics seemed complete until relativity revealed that space and time themselves were participants in the story. We should hold our current understanding of interstellar travel's impossibility with appropriate humility, while being clear-eyed about what the current evidence shows. What the current evidence shows is the barriers are real, they are large, and they are grounded in physics that has been tested to extraordinary precision. Any honest accounting of the situation has to acknowledge that the light speed limit is not a rumor. The energy requirements of relativistic travel are not speculation. The time dilation that separates interstellar travelers from the world they left is not a narrative device. It is what actually happens to time in a universe with a finite speed of light and a flat, four-dimensional spacetime. These are the features of the universe we live in, verified by experiment, confirmed by observation, built into the infrastructure of everything from GPS satellites to particle accelerators. And yet, and this is the note on which it feels most honest to rest, the universe does not owe us a comprehensible answer to the question of why. It did not construct its laws with human ambition in mind. It did not set the speed of light at a particular value because it wanted to limit us. The universe simply is what it is. The laws of physics are what they are. And within those laws, we exist briefly, improbably, and with an awareness of our situation that is, considered carefully, more remarkable than any limitation. We are made of atoms that have existed since the first minutes after the Big Bang. Those atoms were part of exploding stars and drifting gas clouds and the swirling disk of material that formed our solar system. They came together through processes of extraordinary complexity and beauty to form creatures capable of looking back at the universe that made them and asking, how big is this place? How does it work? Could we explore it? Most of it, the honest answer, is no. Most of the universe, the overwhelming, crushing, mind-dissolving majority of everything that exists, will remain forever beyond our physical reach. Not because we haven't tried hard enough, not because we aren't clever enough, but because we are biological creatures with finite lifespans, living in a universe governed by physical laws that enforce a very small speed limit across distances, that laugh at our sense of what large means. But here is the thing about being able to know the size of something, even when you cannot reach it. The knowing is not nothing. The knowing is, in fact, everything. A person who stands at the edge of the ocean and understands that it is 3,000 kilometers to the next continent is not diminished by their inability to swim across it. They are enriched by understanding the scale of what lies before them. They are changed by it. They carry that knowledge with them, and it makes their world larger, not smaller, even if they never cross the water. We carry the universe with us. Not physically, we can't, but cognitively, emotionally, intellectually. We know the universe is 93 billion light-years across in its observable extent. We know it contains 2 trillion galaxies. We know the nearest star is 4.24 light-years away, and that the Milky Way is 100,000 light-years from edge to edge. We know that space itself is expanding, that dark energy is driving the galaxies apart, that the observable universe is slowly becoming less and less reachable. We know that black holes bend time, that neutron stars are so dense that a teaspoon of their material would outweigh every mountain on Earth, that some stars are so large that if you place them at the center of our solar system, they would swallow everything out past Jupiter. We know these things, and the knowing of them, despite our physical confinement, to this one small neighborhood of one ordinary galaxy is one of the most extraordinary achievements of any known form of intelligence in the history of the universe. The stars are not waiting for us, but we are watching them. We are measuring them, characterizing them, listening to the light they send, and interpreting the messages written in that light about their composition, their temperature, their age, their motion. We are, in our own improbable way, filling in the map of a territory we can never visit. And that map, incomplete and approximate as it is the most ambitious intellectual project our species has ever undertaken. You will never leave your cosmic neighborhood. Almost certainly, neither will your children, or their children, or anyone whose lives you will touch in your time here. The Milky Way galaxy, 100,000 light-years wide, and containing more stars than there are grains of sand on all of Earth's beaches, will remain almost entirely unexplored in any physical sense for as far ahead as we can honestly project. The trillions of galaxies beyond our own are beyond reach in an even more absolute sense. The universe, in all its staggering extravagance, is not a place you will travel through. It is a place you will be situated within, and from that situation, from this tiny, miraculous, improbable vantage point on a small rocky planet orbiting an unremarkable star at the edge of an ordinary galaxy, you will look out at all of it and feel whatever it is that humans feel when they confront something that is simultaneously beautiful and overwhelming and permanent and beyond all possibility of being fully known. Maybe that feeling doesn't have a name yet. Maybe it needs one. It sits somewhere between awe and grief, between wonder and humility, between the joy of understanding and the ache of limitation. It is the feeling of knowing exactly how large your cage is and finding, somehow, that the knowledge itself is a kind of freedom. It is the feeling of standing on a beach at night, looking up at a sky full of lights, and knowing, really knowing, with the full weight of science and physics and mathematics, that those lights are impossibly, irreversibly far away, and looking anyway, and being grateful, in whatever way gratitude makes sense for a creature assembled from ancient star stuff, brief and luminous against an infinite dark, for the fact of being here at all,